Welcome to Lecture 9 of our machine learning course. Today we explore reinforcement learning and Q-learning, before looking at multi-agent systems where many agents learn at the same time. First, let's establish the foundations of single-agent reinforcement learning. At its core, reinforcement learning is about an agent learning by trial and error. Actions that move it toward a goal are reinforced, while those that don't are ignored. It's a powerful approach for AI to succeed in unfamiliar environments by balancing short-term sacrifices for long-term rewards. This is the agent environment loop. The agent performs an action, the environment responds with a new state and a reward, and the cycle repeats thousands of times as the agent learns. The goal is to learn a policy, which is the strategy for choosing actions. We want the policy that maximizes the expected sum of discounted future rewards, learned through direct interaction, rather than being told the correct answer. Reinforcement learning stands out because it excels in complex environments that challenge human intuition, it minimizes the need for labeled data, and it optimizes for long-term consequences. Next, let's dive into Q-learning, which is a classic value-based algorithm. Q-learning finds an optimal action selection policy for any finite Markov decision process. It is model-free, meaning it learns the best behavior through repeated interaction without needing to know the environment's internal mechanics. The Q-learning update is the heart of the algorithm. We nudge our old value estimate toward the reward just received, plus the discounted value of the best action available in the next state. The alpha and gamma parameters control how we prioritize current and future information. The agent must constantly balance exploitation, using what it already knows, with exploration, trying random actions to discover better strategies. The epsilon greedy strategy is a standard way to manage this trade-off. Theory guarantees that if you visit every state action pair often enough, the Q values will converge to an optimal policy, eventually stabilizing so that further learning doesn't change them. Here's a quick summary of key terms used in Q learning: Q value, state, action, reward, policy, and learning rate. And here are the remaining key terms: discount factor, episode, exploration, exploitation, the epsilon greedy strategy, and convergence. Now we move to part 3, multi-agent reinforcement learning. In many real-world scenarios, like autonomous vehicles or market trading, we have multiple decision makers. The challenge here is that each agent is learning simultaneously, and their actions directly affect one another. The core difficulty in multi-agent reinforcement learning is that from any one agent's perspective, the other agents are part of the environment, and they keep changing. Because the ground shifts under everyone at once, we need specialized approaches to study learning in this setting. Agents can relate in 3 primary ways: cooperatively, where they share a common goal; competitively, where goals are in direct opposition; or in a mixed relationship, which is the most realistic and complex scenario. Stochastic games, also known as Markov games, provide the formal framework for MARL. They generalize Markov decision processes to multiple agents by tracking states, actions for each player, joint rewards, transitions, and the discount factor. Often, agents cannot see the full global state. In cooperative settings, we use the DEC-POMDP model. Because agents operate on purely local observations, solving these is NEXP complete, highlighting the inherent difficulty of coordinated teamwork. Non-stationarity is the central problem. Because every agent updates its policy simultaneously, the environment dynamics are never static. This violates the assumptions needed for traditional single-agent convergence, meaning yesterday's optimal move might be today's error. Beyond non-stationarity, we also face challenges like credit assignment for shared rewards, scalability as the joint action space grows, partial observability, and the need for agents to coordinate on compatible strategies. To recap, we moved from single-agent RL, where an agent learns through trial and error, to Q-learning for value optimization, and finally to the complexities of multi-agent reinforcement learning. Thank you for joining me for this lecture.